These indicating instruments are giving the operator important information about pressures, flows, temperatures, and levels in various systems throughout the plant. In the last unit, we gave you a general overview of how these instruments work and how measurements are taken in one location and then transmitted to remote locations. We also told you that information can be displayed on gauges or recorders. Without these instruments, you could not run your plant. In this unit, we'll continue our discussion of plant instrumentation by looking more closely at how indicating instruments measure pressure and flow. Knowing how instrumentation works can help you determine what's happening when you see a reading that's unusual. It's often easy to blame the instrument, when in fact, something's wrong in the plant. But if you know how the instrument works, you'll be less likely to make this mistake. We'll begin this unit by looking at the principles behind pressure measurement and how specific instruments used to indicate pressure work. Then we'll do the same thing with flow and show you how pressure and flow measurements are related. Finally, we'll give you some valuable information about protecting pressure and flow instruments to ensure that their measurements are accurate. Okay, before we talk about how an instrument measures pressure, we need to review some of the principles of what pressure is and how it's measured. Stated simply, pressure is the force that's exerted on a surface. By now, you know that there is a formula that can be used to determine pressure. The formula states that pressure, P, is equal to force, F, divided by area, A. So, if you know both the force exerted on a surface and the area of that surface, you can determine the pressure. The resulting pressure can be expressed in a variety of ways. One of the most common units for pressure is pounds per square inch, or PSI. In the metric system, pressure is usually expressed in kilopascals. Let's see how the formula and units are applied by looking at an example. We'll use this clear container. Our object is to put water into the container and then, using the knowledge that pressure equals force divided by area, determine how much pressure is exerted on the bottom of the container. To do this, we'll need to know the force exerted by the water and the area of the bottom of the container. We've already determined the area of the bottom. It's 20 square inches. Now we need to find out how much the container weighs. And you'll see why we need to do this in just a few moments. We'll put this container on the scale, and we see that the container weighs 1 pound, 5 ounces. Okay, we'll put some water in the container, and we've colored the water to make it easier to see. Now, we have to figure out how much force the water is exerting on the bottom of the container. We already know that the force exerted by the water is equal to the weight of the water. So, all we have to do is weigh the container of water. Then, by subtracting the weight of the container, we can determine the weight of the water. The container and the water weigh 10 pounds. Next, we subtract the weight of the container, which is 1 pound, 5 ounces, and 1 pound, 5 ounces from 10 pounds leaves 8 pounds, 11 ounces. And that's about 8.7 pounds. So, the force exerted by the water is approximately 8.7 pounds. Since that 8.7 pounds is exerted over an area of 20 square inches, we divide 8.7 by 20 in order to get the pressure expressed in pounds per square inch. Doing the math, we get approximately 0.43 pounds per square inch. And this is the pressure on the bottom of this container. From this example, we can see that the pressure exerted on the bottom of the container depends on the weight of the water in the container and the area of the container's bottom. But we don't know how the volume of the container affects pressure. We'll look at the effects of volume using this smaller container. It has a lot less volume than the first one. And this time, the area of the bottom is 10 square inches, and the weight of the water is 4.3 pounds. If we plug these figures into our formula, we get the force, which is 4.3 pounds divided by the area, which is 10 square inches. Again, we do the math and find that pressure in this container is equal to 0.43 pounds per square inch. The pressure at the bottom of each container is the same, even though both containers are different in size and volume. From this, we know that pressure does not depend on the size or volume of a container. We can see what it does depend on if we figure out what each container has in common. Well, you may have noticed that the height of water in each container is the same. This is a significant point because, as it turns out, the pressure exerted by a water column is dependent not on the volume, but on the height of the water. The height of the water in each of these containers is 1 foot, and we found the pressure in each case was 0.43 psi. We can then conclude that a column of water 1 foot in height exerts a pressure of 0.43 psi. This is a good number to remember because we'll be using it again. Now, you already know that the pressure resulting from the height of a fluid in a container is called static head. What we've determined so far is that the pressure exerted at the bottom of a tank depends on static head, not the size of the tank or the volume of the tank. The reason for this is pressure is measured per unit area. It doesn't matter how many units there are. It could be 100 square inches or 10 square inches. What matters is how much fluid is above each unit. Now, we can take this one step further and say that the pressure exerted at any point in a column of fluid depends on the height of the fluid above that point. Let's look at an example of this. Now, here's a column of water that's 5 feet in height. We know, from what we've done so far, that the pressure of a 1 foot column of water is 0.43 psi. So, a 5 foot column exerts 5 times that, or approximately 2.2 psi. The gauge connected to the bottom of this column shows this is true. Now, what about the pressure 2 feet from the bottom? What should it be? Well, I'm moving this gauge to a place 2 feet from the bottom. Let's see if we can figure this out. In a 5 foot column, there are 3 feet above the point that we're measuring. And 3 times 0.43 equals approximately 1.2 psi. The gauge at 2 feet above the bottom should read approximately 1.3 psi. And as you see, it does, just as we predicted. This demonstrates that the pressure at any point in a column of water depends on the amount of water above that point. Okay, what have we learned so far? We've learned that pressure is the amount of force that is exerted on a given surface. And we've also learned that the formula P equals F divided by A can be used to determine pressure. We've also learned that the pressure exerted by a fluid does not depend on the volume of the fluid, but rather on the height of the fluid above the point where the pressure is being measured. Finally, we've learned that a column of water with a static head of 1 foot of water exerts a pressure of 0.43 psi. Now, there's a lot more about pressure that you need to learn. But before we go on, make sure you understand this information by reading the textbook and answering the questions at the end of the segment. If you have any questions, your instructor can help you find the answers. In the last segment, you learned that the height of a column of fluid determines the pressure exerted by that fluid. You also learned that the pressure exerted at any point along a column of fluid is determined by the height of the fluid above that point. Now, while everything that we've told you is correct, we haven't looked at the entire picture. So far, we've looked at pressure in general and ignored atmospheric pressure. In this segment, we'll consider atmospheric pressure. In earlier topics, you learned that the Earth is surrounded by air, which exerts a force on the Earth's surface. Atmospheric pressure varies depending on weather conditions and how high above sea level it's being measured. The weatherman on the news generally tells you the daily atmospheric pressure for your area. At sea level, for example, the atmosphere exerts a pressure of approximately 14.7 pounds per square inch. Now, you usually don't notice the pressure of the atmosphere because you're used to it. However, it is there, and if atmospheric pressure increases or decreases, you can sometimes feel it. Let's make this clearer by considering this example. When you're standing on the deck of a swimming pool, the atmosphere is exerting a pressure on you. Now, as we've said, you don't notice it because you're used to it. You take it for granted it's there. But if you dive into the pool, you will immediately notice that there's an increase in pressure. As you go deeper under the surface of the water, your ears sense the added pressure, and you feel a pressure on your chest. The reason for this is that you now have two pressures working on you, the atmospheric pressure plus the pressure of the water. If you want to know the total or absolute pressure that's being exerted on you while underwater, you take the atmospheric pressure and add 0.43 psi for every foot of water above you. If there is 1 foot above you, then 14.7 psi plus 0.43 psi equals approximately 15.1 psi of absolute pressure that you are feeling. When we refer to absolute pressure, we mean the total pressure exerted, including atmospheric pressure. Now, some of the pressure gauges in your plant do what we did in the last segment. That is, ignore the fact that atmospheric pressure is exerting a force. This gauge, for example, is measuring the discharge pressure from a condensate pump. Its measurements do not include atmospheric pressure. You know this because the gauge is marked PSIG. The letter G stands for gauge. On the other hand, some of the gauges in your plant do include atmospheric pressure in their measurements, in the same way that we did in the pool. This gauge, showing main condenser pressure, includes atmospheric pressure in its measurements. You know this because the gauge is marked absolute. Other absolute gauges may be marked PSIA. The A in this case means absolute. Now, occasionally, you'll find gauges that are simply marked PSI. In situations like this, you must check with your supervisor to make sure what type of pressure the gauge is measuring. The relationship between gauge pressure, PSIG, and absolute pressure, PSIA, can be easily seen if we visualize it on a graph. This line represents pressure, a force exerted on a surface. Absolute pressure begins at 0 PSIA, where no pressure is being exerted, and increases in this direction. Zero gauge pressure begins at atmospheric pressure and increases in this direction also. At sea level, 0 PSIG occurs at 14.7 PSIA. The absolute scale is the standard for all pressure measurement. In our example, we showed you how gauge pressure related to absolute pressure. We could just as easily have shown you how inches of water, inches of mercury, or any other units of pressure related to absolute. For example, a 1-foot column of water exerts a pressure of about 0.43 psia. The conversion factor, then, is 0.43 psia for every foot of water. If you're measuring in inches of mercury, the conversion factor is 0.5 psia for every inch of mercury, because a 1-inch column of mercury exerts a pressure of about 0.5 psia. We've rounded off these numbers to make our calculations easier. But you must keep in mind that while approximate is good enough for what we're doing, in the plant you'll need to use exact figures for any calculations you make. So far, we've primarily been discussing pressures above atmospheric, or positive pressures. But pressure exists below atmospheric. This we call negative pressure. The reference point on the absolute scale is atmospheric. Pressures above atmospheric are positive. Pressures below atmospheric are negative pressures, even though they may be expressed in positive values. For instance, 2 psia is a negative pressure because it is less than atmospheric pressure. Negative pressures can be talked about in two ways, as vacuum or as back pressure. The condenser is one of the most common places in the plant where there is negative pressure. You may hear both of these terms used to describe condenser pressure. But while vacuum and back pressures are measures of negative pressure, they're not the same, and you need to know the difference between them. Basically, vacuum is pressure below atmospheric that is measured from atmospheric pressure downward, while back pressure is a pressure measured from 0 psia upwards. We'll use our standard, the absolute pressure scale, to show the difference between vacuum and back pressure. Vacuum or back pressure can be measured in many different units, such as psia, minus psig, feet of water, or inches of mercury. We'll use inches of mercury for our example. 1 inch of mercury is equal to about 0.5 psia. Both vacuum and back pressure are measured only between 0 and 14.7 psia. So, we must first determine the number of inches of mercury between 0 and 14.7 psia. We do this by dividing 14.7 by 0.5. We get about 29.5. We rounded numbers off so that the numbers we're using are approximate. So, there's approximately 29.5 inches of mercury between 0 and 14.7 psia. Now, the key to understanding vacuum and back pressure is knowing which way each is measured. Let's look at vacuum first. Vacuum is measured from atmospheric pressure downward. This means that at atmospheric pressure, vacuum is 0 inches of mercury. Vacuum increases as absolute pressure decreases, so that at about 0 psia, vacuum is approximately 29.5 inches of mercury. Back pressure is just the opposite. It's measured from 0 psia upward. This means that at about 0 psia, back pressure is 0 inches of mercury, and at 14.7 psia, back pressure is approximately 29.5 inches of mercury. As absolute pressure increases, so does back pressure. Okay, now that you know that absolute pressure and gauge pressure have equivalent values, and that there are a number of ways to measure pressure, and that pressure can be both negative and positive, there is one more principle of pressure measurement that we need to talk about. That's differential pressure. This will become very important later on when we talk about flow measurement. Let's go back to our graph. Let's consider 2 points on the absolute pressure scale. This one at 20 psia we'll call point A, and this one at 4 psia we'll call point B. If we want to find out the difference in pressure between point A and point B, we will subtract 4 psia from 20 psia. This would show us that there is a difference in pressure from point A to point B of 16 psia. Now, it doesn't matter if we use the absolute scale or the gauge scale. Differential pressure simply means the difference in pressure between any 2 points. Differential pressure can be expressed in many different units, but the two most common are pounds per square inch differential, abbreviated PSID, and delta P. As with gauges that measure absolute and gauge pressure, sometimes gauges that measure differential pressure are simply marked PSI. Once again, it's important that you check with your supervisor to find out what the gauge is measuring, so that your readings will be accurate. One of the most common places where you will see differential pressure used is to measure the pressure across a strainer or filter. As the strainer does its job, trapping particles, differential pressure across it increases. Eventually, at a certain differential pressure, usually indicated in the manufacturer's specifications, flow is restricted to the point that the strainer or filter must be cleaned or changed. It's the differential pressure, or delta P indication, that alerts the operator to the problem. Okay, the last 2 segments have dealt with the principles of pressure measurement. We've shown you how pressure is measured using gauge and absolute. We've also shown you that pressure can be both negative and positive, and that a negative pressure can be expressed as both a vacuum or a back pressure. Finally, you learned that differential pressure is the difference in pressure between 2 points. In the next segment, we'll show you how these principles apply to specific pressure measuring instruments that you'll find in the plant. For now, read the material in the text and answer the questions. If you have any trouble understanding this information, ask your instructor to help you. So far in this unit, we've shown you the different ways that pressure can be measured. We've talked about gauge pressure, which doesn't include atmospheric pressure in its measurements, and we've talked about absolute pressure, which does include atmospheric pressure in its measurements. We've also told you that differential pressure is the difference in pressure between two designated points. In this segment, we want to show you how some of the most common pressure measuring instruments work and the types of measurements you can get from them. Let's begin by discussing one of the simplest devices for measuring pressure, the manometer. A simple manometer is nothing more than a U-shaped tube that contains a fluid and is open at both ends. This particular manometer contains water. We've colored the water red so it shows up better. Manometers work on the principle that any difference in pressure between the two ends will cause the fluid column to be pushed towards the end with the lowest pressure. Right now, both ends of this manometer are open to the atmosphere. This means that atmospheric pressure is being exerted on both ends of the manometer, resulting in a zero pressure differential. Since the pressure exerted on each end is equal, the column of water is exactly centered in the tube. This also means that the height of the liquid on each side of the tube is equal. If we want to use this instrument to measure pressure, in a pipe for example, we would connect one end of the manometer to the pipe and leave the other end open to the atmosphere. Then, by using some simple calculations, we could determine the pressure differential between the pipe and atmosphere. Now here we have a line which is connected to a pressure source. Right now we have a valve closed, so there's no pressure in this line. We'll hook it up to the manometer. Then, as we open up the valve, watch what happens to the water in the manometer. Notice, when pressure increases, the water level of both ends of the water column changes. The water is being pushed away from the left-hand side of the manometer that's connected to the pressure source. The level will continue to change until the pressure exerted by the weight of the rising column equals the pressure exerted by the source. At that point, the water column stops moving. We know that the pressure we're measuring is greater than atmospheric because the water moved away from the end connected to the source. However, in order to determine how much greater the pressure is, we must first determine the difference in the heights of both ends of the water column. We can do this by measuring this difference with a ruler. This distance is the height of the column which is being held up by the pressure. Then, with a simple calculation, we can determine what the pressure is. In this example, the difference in height of both ends of the column is 12 inches. So, the pressure difference is 12 inches of water. This can also be converted to pounds per square inch by multiplying the height of the water column in feet times 0.43. Since the height in our example is 1 foot, 1 times 0.43 equals 0.43 psig. The pressure exerted by the source is 12 inches of water, or 0.43 psig. Now, it won't be necessary for you to carry a ruler around with you to take readings from manometers in the plant, because there is usually a scale marked off on or near the column of liquid. In this example of a manometer connected to a main lube oil tank, 0 is marked on the scale at the point where both ends of the water column will be when the manometer is under an equal pressure. The scale progresses both above and below 0 and is measured in inches. To read the scale, you simply add the reading from both ends of the water column. In the case of this example, one end of the column of water, the one above 0, reads about 1/2, and the other end of the column, the one below 0, reads about 1/2 as well. Both readings above and below 0 should be the same. Otherwise, there isn't enough liquid in the manometer and the readings won't be accurate. To determine the height of the column supported by the pressure, we add both readings above and below 0, and we get 1 inch of water. Since this side of the manometer is connected to the main lube oil tank, and because the column of water moved this way, we know that the pressure in the lube oil tank is lower than atmospheric. In fact, it's 1 inch of water lower than atmospheric. Well, this pretty much covers how to read a manometer. We'll stop here and let you review the text and talk with your instructor. When we return, we'll talk about another type of manometer that uses a liquid other than water. In the last segment, we talked about manometers, which use water as the measuring fluid. Well, imagine how large the water manometer would have to be to register a pressure differential of 100 psi. This could create a problem for the operator because the level of water would be over 230 feet high. But this problem can be solved by using a heavier liquid, since a heavier liquid exerts more pressure than a lighter one. This means that in order to exert the same pressure, the heavier liquid requires a smaller column height than a lighter liquid. A heavier liquid often used instead of water is mercury. A 1-foot column of mercury exerts more than 5 times greater pressure than a 1-foot column of water. Let's look at an example of a mercury manometer. Here is a mercury manometer with the left-hand side hooked up to a pressure source. Because the mercury has moved towards the open end, the right-hand side, we know that the pressure in the pipe is greater than atmospheric. Like most other manometers, this one has a scale marked off in inches. Using it, we can see that the difference in heights of the two columns is 9 inches, 4.5 inches above zero, and 4.5 inches below zero. The pressure is supporting a 9-inch column of mercury. To find out how much pressure the 9 inches represents, we multiply 9 times 0.5. Doing the math, we get 4.5 pounds. Pressure in the pipe is 4.5 psig. The reason it's psig is because one end of the manometer is open to the atmosphere. Now, one of the most common uses of a mercury manometer is a special type called a barometer. Atmospheric pressure varies with several factors such as height above sea level and weather conditions. A barometer is the instrument used to measure atmospheric pressure. A typical barometer works like this. One end is sealed and contains a pressure of 0 psia. The other end is open to atmosphere. Atmospheric pressure pushes the mercury up the barometer tube until it reaches a point where the pressure exerted by the mercury column equals the pressure exerted by the atmosphere. At sea level, the column of mercury will be approximately 29.5 inches. Another common use of a mercury manometer is to measure vacuum in a condenser. It looks a lot like a barometer, except that one end of the manometer is connected to the atmosphere, while the other end is connected to the condenser. The scale reads from 0 inches of mercury at the bottom to approximately 30 inches of mercury at the top. If there is no vacuum in the condenser, the manometer will read 0, because the pressure at both ends of the manometer is the same. But if the condenser has a vacuum, there will be a difference in pressure between both ends of the manometer. Atmospheric pressure will push the mercury towards the lower pressure end connected to the condenser. The greater the condenser vacuum, the higher up the mercury will be pushed. Operators use a vacuum manometer and a barometer to calculate condenser back pressure. Usually, the manometer for condenser vacuum is located right next to the barometer. All you have to do to find back pressure is to read the two. The difference between the condenser manometer reading and the barometer reading is the back pressure. In this case, the condenser manometer is reading 28, while the barometer is reading 29.5. 29.5 minus 28 equals 1.5. The back pressure is 1.5 inches of mercury. If you want to know how many psia this is, you would multiply it by 0.5 to get an approximate answer. The back pressure is approximately 1.5 inches of mercury, or 0.75 psia. Now that you've seen how vacuum is measured and back pressure is calculated, let's look at some other instruments that can be used to measure pressure. These include a Borden tube gauge, a bellows gauge, and a diaphragm gauge. You've already seen how a Borden tube gauge works, but let's have a quick review and then we'll spend more time on the other types of gauges. Inside a Borden tube gauge is a curved tube that is sealed at one end. When pressure is applied to the tube, it attempts to straighten the tube out. The greater the pressure, the more the tube tries to straighten. The movement of the tube is transferred to the pointer on the gauge by mechanical linkage. When pressure decreases, the tube returns to its original shape. All Borden tubes work on this principle of trying to straighten out a curved tube. However, the design of the tube may vary. The tube may be C-shaped, helix, or spiral. But for most applications, the principle is the same. Pressure in the tube will cause it to move, and mechanical linkage is used to transfer this movement to a pointer. Borden tube gauges are most often used to measure gauge pressure. Typically, Borden tubes are not designed to measure pressures less than 20 pounds. A second type of gauge that is often used in the power plant is the bellows gauge. With this type of gauge, we can measure gauge pressure, as well as differential pressure and absolute pressure. The inside of a typical bellows gauge looks like this. Here's the bellows. Notice that it is sealed at one end, just like the Borden tube that you just saw. The pressure to be measured enters here. As pressure increases, the bellows expands. This movement causes a mechanical linkage to operate the pointer. When pressure decreases, the bellows returns to its original position, and the mechanical linkage repositions the pointer. Bellows gauges are not as rugged as Borden tube gauges, and for this reason they're usually designed to measure pressures less than 50 psi. The final pressure measuring device that we'll discuss is the diaphragm gauge. They work something like bellows gauges, except that instead of the bellows, a flexible diaphragm is used. On one side of the diaphragm, a pressure is exerted. On the other side of the diaphragm, a connecting rod is attached to the gauge pointer. When pressure enters the gauge, it causes the diaphragm to move. This, in turn, moves the connecting rod and pointer. The greater the pressure, the greater the movement of the diaphragm and pointer. Diaphragm gauges are extremely accurate instruments for measuring pressure, vacuum, or differential pressure. When measuring differential pressure with a typical diaphragm gauge, the two pressures are exerted on opposite sides of the diaphragm. We'll label this side A, and this is side B. When the pressure on both sides is the same, the pointer is in the middle. If pressure on side A is greater than side B, the pointer moves this way. If the pressure on side B is greater than side A, then the pointer moves this way. Now, too great a pressure, or vacuum, can cause the diaphragm to rupture. So they're usually not used for measuring high pressures. However, since the diaphragm is easily moved by the smallest amount of pressure, they have great application for low pressure readings. So, now you know how pressure is measured and some of the most common devices used in pressure measurement. This is a good place to stop so that you can read the text and answer the questions. Remember, if you have any questions, clear them up with your instructor before going on. When you come back, we'll take a look at flow and the instruments that we have for measuring it. The first four segments of this unit have dealt with pressure and the way it's measured and displayed by the indicating instruments in a plant. In this segment, we'll turn our attention to measuring flow rate and the instruments in a plant which measure flow. In your plant are hundreds of feet of pipe through which a number of fluids such as water, steam, and air constantly flow. You depend on the flow of these fluids to keep your units operating efficiently. Flow is needed to supply boilers with water, turbines with steam, lubricating systems with oil, and so on. Without flow and flow measurement, your plant would have to shut down. Now, you may be wondering what pressure and flow have to do with each other. Well, without pressure, flow would be impossible. In fact, flow is caused by a difference in pressure. And as we'll see in a few moments, this difference in pressure is one of the things that helps us measure flow. But first, let's make sure you know what flow measurement is. Flow measurement is defined as the measure of the amount of fluid that passes a point during a specific period of time. Some typical units are gallons per minute, cubic feet per minute, and pounds per hour. Now, you can talk about flow in two ways, mass flow and volumetric flow. Mass is anything that has weight. So mass flow is the mass of fluid passing a given point in a given period of time. A typical unit of measurement of mass flow is pounds per hour. Volume, on the other hand, is that area that is taken up by mass. So, volumetric flow is the volume of fluid that passes a given point in a given period of time. Typical units for measuring volumetric flow are gallons per minute or cubic feet per minute. Since volumetric flow is a direct way of measuring the flow rate of a fluid, we'll consider it first. Then we'll cover mass flow measurements. One of the simplest instruments used to measure volumetric flow is a positive displacement flow meter. Now, there are many ways to design one of these meters, but this is a typical example. The meter is actually a counter that is connected to a rotating device that resembles a paddle wheel. Each section of the paddle wheel holds a known volume of fluid. When this instrument is installed in the flow path of a fluid, the fluid fills up each section of the paddle wheel, causing the wheel to rotate. The meter counts the number of times that the wheel rotates. Since each turn of the paddle wheel represents a known volume of fluid, counting the number of times that the wheel rotates over a given period of time will give you the flow rate. Positive displacement flow meters can be found in a variety of locations in a plant. This positive displacement meter is measuring the volume of fuel oil going to the boiler. A second instrument that can be used to measure a volumetric flow rate is a rotometer. Like positive displacement flow meters, there are a number of ways that a rotometer can be designed. In this typical example, the rotometer contains a metal float located inside a tapered vertical tube. On the tube is a scale that is marked off in gallons per hour. When fluid flows through a rotometer, it lifts the metal ball. You then read the mark that corresponds with the middle of the metal ball. In this case, that's about 13 gallons per hour flow. Volumetric measuring instruments like positive displacement flow meters and rotometers are very accurate ways of measuring flow rates. However, they do have some limitations. One of the limitations is size, since these meters must be sized to accommodate the volume of fluid flowing through them. They're not practical for measuring extremely high rates of flow. The meter itself would have to be too large to be practical. For situations like these, it's necessary to measure flow by another means. The most commonly used method is to measure the mass flow rate. In the plant, flow restrictors are commonly used to measure the mass flow rate of a fluid. Flow restrictors cause the opening where the fluid is flowing to become smaller. Now, as you know, a pressure drop results when flow is restricted. This pressure drop, or differential pressure, across the restrictor can be measured, and from it, the mass flow rate can be calculated. The formula that is generally used to calculate mass flow rate states that mass flow, m, is equal to a constant times the square root of the differential pressure. A typical, though highly simplified, mass flow measuring system looks like this. The components include a flow restrictor, a differential pressure measuring device, and a square root extractor. When flow is established in the system, the flow restrictor creates a small differential pressure which is measured by the differential pressure measuring device. Since flow is proportional to the square root of the differential pressure, this measurement must be processed by the square root extractor. A square root extractor is nothing more than a fancy calculator that computes a signal proportional to the square root of the measured differential pressure. Let's see how the flow restrictor and its flow measurement components fit into a typical instrumentation system. The output of the square root extractor is sent to a transmitter. The transmitter sends a signal to remote indicators. The system may also operate an alarm. In this way, flow measured in a pipe is sensed and displayed wherever it's needed. Condensate and feed water flow, as well as main and auxiliary steam flow, are all measured this way. So you will need to be able to locate and recognize this type of instrumentation. Okay, let's return to flow restrictors. There are three basic types of flow restrictors that are commonly used for measurement. They are the venturi, the orifice, and the elbow. Let's look at each of these and see where the measurements for differential pressure are taken. The most accurate mass flow measurements are made by using a venturi. A venturi is a tapered restriction like we've been looking at. The narrowest part of the venturi is called the throat. Pressure readings are taken upstream of the venturi and at the throat. The venturi is designed to create a minimum of turbulence, which could affect the accuracy of a measurement. One example of a large venturi is the one found on some condenser circulating water systems. They're used to measure flow at the pump discharge. A second restrictor that is often used is an orifice. An orifice is a plate with a hole in the middle that is smaller than the pipe in which the orifice is installed. Pressure readings are taken from the upstream and downstream sides of the orifice. An orifice is not as accurate as a venturi, but it is much less expensive to manufacture and is used widely in power plants. Here's an example of a typical orifice in the plant used to measure steam flow. The final type of flow restrictor that we'll look at is the elbow. An elbow creates a differential pressure by causing the fluid to change direction. Pressure readings are taken from the outside and inside of the elbow. Since elbows create a great deal of turbulence, their readings are not very accurate. Readings taken from elbows are primarily used simply to indicate whether or not there is flow in the pipe. Flow indicating elbows look like this from the outside. Well, you now know the two methods that are used to measure flow. You also know that a relationship exists between pressure and flow. Without pressure differential, flow is impossible. This is a good place to stop so you can read the material in the text and answer the questions. If you have any problems, ask your instructor. We've covered a lot of material in this unit on pressure and flow measurement. You know how both pressure and flow are measured. But before we leave this unit, you need to know what you can do to keep the plant's pressure and flow measuring instruments operating in good order. For the most part, pressure and flow measuring instruments are pretty reliable. As long as they get periodic servicing by the instrument department, you can be assured of getting proper readings. However, keep in mind that these are precision instruments and will not take a great deal of abuse. Now, the first example of instrumentation problems that we're going to look at, you probably won't find very often. It's a gauge that is off scale. While this is not a common problem, if it occurs, you need to recognize what to do about it. You'll know this has happened when you see the pointer at full scale or up against a peg on the scale face. If during your routine checks of the instruments in the plant, you find a gauge that is continually showing maximum pressure or is off the scale entirely, your first action should be to isolate the gauge from the system. This is usually done by closing a valve on the supply line. Once this is done, you should inspect the system and make sure that it is operating normally. This may involve checking another gauge upstream or downstream of the one that is off scale. In this case, the operator discovers that the actual pressure is too high for the gauge, which was off scale. So, he reports it to the instrument department so that they can replace it with one designed to handle the pressure. An instrument technician will then be sent to replace the gauge. Now, while a gauge that is off scale is not that common an occurrence in the power plant, there are certain situations that can cause a gauge to go off scale for a short period of time. This can damage the internal parts of the gauge and make its measurements inaccurate. A good example where this can occur is when valves in a gauge line are opened in order to put the gauge in service. If the supply valve is opened too quickly, a violent pressure shock occurs. This may send the gauge off scale and damage the gauge. So, if you are in this situation, make sure that you open gauge supply lines slowly so that sudden pressure exerted on the gauge does not damage its internal parts. If you should ever accidentally peg a gauge off scale, make sure you report it to the instrument department so that they can check it out and take any action that they deem necessary. A third situation that you may find in the plant is a chattering gauge. Just like a gauge that is forced off scale, a chattering gauge can damage the internal parts and provide you with inaccurate readings. If the chattering is caused by undesirable fluctuations in the signal to the gauge, it can usually be controlled by adjusting or throttling the supply line until the chattering stops. If this doesn't work, then you better call the instrument department so they can find out the problem and correct it. Until this is done, you should suspect the accuracy of any reading taken from this gauge. The final way of protecting a gauge that we'll look at is the seal loop. Seal loops are used to protect gauges from the intense heat of steam. Basically, all a seal loop does is allow steam to condense and form a water seal between the steam and the gauge. This keeps the steam from coming in direct contact with the gauge, preventing the gauge from being damaged by excessive heat. Well, we've come to the end of another unit. You've learned that pressure can be measured in many ways, and that there are a variety of instruments used to display pressure measurements. You've also learned that flow measurement can be volumetric or mass, and that there are a number of instruments used for each type of measurement. Finally, you've seen that gauges must be protected to ensure accurate readings. Stop the tape and read the material in the text and answer the remaining questions. If you have any questions about the material we've covered, ask your instructor to assist you.